Okay, so for the next problem in experiment number 10, we're asked to consider the Lewis structure of carbon tetrafluoride and also draw the 3D model and answer a few additional questions about the bond angle and polarity of this structure. So, if we first draw the Lewis structure, we know that the first thing that we have to do is count up the total number of valence electrons in the molecule. So for carbon, we know that there is one of them from the formula, and carbon is in group 4, so we know it has 4 valence electrons. For the fluorine, we know that there are 4 of them, and fluorine is in group 7, so each of them have 7 valence electrons. So when we add these up, we know that when we're finished, we should have 32 valence electrons drawn. So the second step is to determine what is your central atom and what is your terminal atoms, and again, remember, it's generally written first, the exception being carbon. So in this, or the exception being hydrogen. So in this case, carbon is the central atom, and it is surrounded by the 4 fluorines. So that's step 2. Now the third step is to draw a single bond from your central atom to all of your terminal ones. So I draw a single bond from each of the carbon to each of the fluorines. So step 3 is done. Step 4, we need to give an octet to our terminal atoms. So for this one, we know that fluorine wants 8, so we have to draw 6 additional dots, or 3 lone pairs, around each fluorine in order for it to have an octet. So once we've done that, then we need to say, okay, how many of our 32 dots have we drawn? And if we look, we see that we've drawn all 32 of them. So we have to consider, okay, all of my fluorines have an octet. I've used all 32 dots. Does my carbon have an octet? And what you see is that fluorines are good to go, and carbon has 4 around it, or 4 bonds, which means that it has 8 electrons, which is an octet. So therefore, you know that this is the Lewis structure for carbon tetrafluoride. Now, in terms of the 3D model, we have to look at the central atom and say how many regions of electron density are around the carbon. And what we see here is that there are 4 regions around the central atom. And when we consider 4 regions, we have to look at what kind they are. Are they all bonding? Do we have any lone pairs? And what you see is from the Lewis structure, all of the regions of electron density around the carbon are bonding. So we have 4 bonding pairs. So if we look at what we know about 3D models, we know that when there are 4 regions around the central atom, we have 3 different possibilities for its geometry. But because that they're all bonding pairs, we know that the geometry of this molecule has to be tetrahedral. So all bonding means we have to have a tetrahedral geometry. And if we think about tetrahedral molecules, we know that they have a bond angle of 109.5 degrees. Now, when we go to draw and generate the 3D molecule, we have to draw this molecule indicating 3 dimensions. That's the whole point. And when we have a tetrahedral molecule, or something with 4 regions of electron density around the central atom, we always have our central atom, and there are 2 bonds that are in plane, or planar. They're flat. We always have 1 bond that comes out of the plane, meaning it comes towards you, and 1 that goes behind the plane, which means it goes behind you. So with this, because we have a tetrahedral molecule, we need to draw our central atom with 2 bonds in plane, 1 coming out, and 1 going behind. So we've got our bonds down, and what this is showing is this is actually showing, as best we can, the bond angle of 109.5 degrees apart. So once we do that, then we put in our terminal atoms. And if you recall, we do not have to write the lone pairs on the terminal atoms, only the central. So if we look at this, we see, okay, we've drawn our central atom, we have all of our bonds correctly drawn, and we put our terminal atoms in. So this is a tetrahedral molecule of carbon tetrafluoride. This is the 3D model. Now, one of the questions asks you whether or not this molecule would be polar. Okay, so when we consider a molecule in its polarity, we have to look at its bonds. And what we see in this molecule is that all of the bonds are carbon and fluorine. So we know that this is a polar bond because we know that fluorine does not have the same electronegativity as carbon. Therefore, the electrons in this bond will not be shared equally. In fact, they will be shared unequally, where they hang out primarily on the fluorine, and since they're not on the carbon, we have a partial positive over here. So we generate a dipole moment. Now, we have to look at this in the molecule and see, okay, we have polar bonds, but what is the polarity of the molecule? Because we have to take it a step further. So if we draw all of our dipole moments for this molecule, we look and see, okay, I have all of these. And remember what I said about polar molecules. You kind of want to think of it as a tug-of-war game. If you don't get moved in any one direction, meaning you have no net dipole moment, you're a non-polar molecule. But if you are pulled in one direction for your molecule, that means you have a net dipole moment and you are polar. Now, looking at this molecule, you can see that this has polar bonds. And if we consider the molecule itself, it looks pretty clear that since all of the bonds are 109.5 degrees apart, they all go in opposite directions, and therefore they all cancel themselves out. So this would be a non-polar molecule. So even though we have polar bonds, we are a non-polar molecule. Now, from this second example, we looked at polarity of a molecule, and we're looking at it here. And what you can see is that determining whether or not we have a net dipole moment can be a little bit difficult at times. And one of the things that makes it easier on you in order to determine whether or not you have a net dipole moment is to look at a few things. So I'm going to go over those now. So when we have a non-polar molecule, we can either have non-polar bonds or polar bonds. When we have a polar molecule, we have polar bonds. Now, this is going to be one of the things that helps you to narrow it down as to what your molecule, the polarity is. Now, polar molecules means we have a net dipole moment. Nonpolar molecules means we have no net dipole moment. Now, I mentioned that determining whether or not you have a dipole moment is difficult. So here is a few little tricks that will assist you in figuring out whether or not you have a net dipole moment. So the first thing you want to do is you want to look at the central atom and you want to say, are there any lone pairs? Now, if your answer is yes, then you are a polar molecule. If your answer is no, you have to keep going. And it doesn't matter if there's one lone pair, two lone pairs, three lone pairs. If there's any lone pairs, the answer is yes, then you have a polar molecule, which means that you have a net dipole moment. Now, the next thing that you have to ask about the molecule is, do you have a different atom bonded to the central atom? The answer is yes, then you are polar. The answer is no, then you have to keep going. And what do I mean by that? Well, say for example we have carbon bonded to fluorine, 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 and then a chlorine. Clearly you can see that the chlorine is the different atom. That's what I mean by, is there a different atom bonded to the central one? Basically what that's saying is that you're going to get a net dipole moment. Your molecule is going to be pulled to one side due to differences in electronegativity. So these are two things that you have to look at that make it a little bit easier on determining whether or not you have a net dipole moment. Now the third thing you have to look at is the 3D structure. And this one's going to become important, especially with the next example that we do. So what you want to go through is when you're determining molecular polarity, you want to look at these three things. And you want to go through, and what you're essentially doing though is determining, do I have a net dipole moment? If so, I am polar. Do I not have one? If so, I am a non-polar molecule. So if we go up and look at carbon tetrafluoride, we see, do I have a lone pair on the central atom? The answer is no, so I keep going. Do I have a different atom bonded to the central atom? No, they're all fluorines, so I keep going. I look at the 3D structure, I see that it's tetrahedral, they're all 109.5 degrees apart. So when that happens, I know that I do not have a net dipole moment and I am a non-polar molecule.